In 1997, a section of Indonesian swampland quietly vented more carbon in 3 months than all of Europe releases in an entire year. This event was not predicted. No models had accounted for it. Then, in 2015, it happened again. Only this time, the failure was global. 3 different continents experienced simultaneous breakdowns through entirely distinct mechanisms. Now, NOAA is projecting a super El Niño for 2026, one that could eclipse the intensity of both its predecessors. Here lies the detail that should give us pause. The forests it is poised to strike are in a more fragile state than they have ever been before such an event. This is not merely a story about weather. It is a story about the singular, complex system that keeps our world habitable, and whether it can endure what is coming. The event itself has yet to reach its peak, and as the data from our planet's forests continues to arrive, the implications become increasingly difficult to ignore. We invite you to continue this exploration with us here at Calm Space. There is a number, 2.75, currently sitting in a government database that remains largely undiscussed outside a small community of atmospheric scientists. And yet, to truly grasp its meaning is to understand a profound shift in our planet's equilibrium. This figure, 2.75 of a degree, represents the upper forecast for what oceanographers call the NIñO 3.4 region. This expanse of the Central Pacific Ocean functions as a thermostat for the entire global climate. According to the National Oceanic and Atmospheric Administration, there is a 61% probability that this region will cross the Super El Niño threshold by July of 2026. This isn't a forecast for a moderate or even a strong event, but a super event, an anomaly of a magnitude we have only clearly documented twice in the modern instrumental record, during 1997 to 1998 and 2015 to 2016. What makes this particular number so deeply concerning? Each time an event of this scale occurs, the headlines seem to write themselves. We read of devastating floods in Peru, severe droughts across Indonesia and Australia, and dense wildfire smoke blanketing cities throughout Southeast Asia. We see reports of mass coral bleaching across the tropics. You have likely encountered this narrative before, or at least a version of it, as has the media ecosystem that reports on climate and weather. This coverage is not inaccurate. Those events will happen. They are real, and their impact is tragic, deserving of every bit of attention they receive. But there is another story unfolding beneath the headlines, one that is invisible, slow-moving, and in many ways, far more consequential than anything you will see on the evening news. Every year, human activity releases between 37 and 40 gigatons of carbon dioxide into the atmosphere. A gigaton is 1 billion metric tons, a number so vast it is nearly impossible to comprehend. To offer some perspective, imagine every car, airplane, factory, and power station on the planet operating non-stop 24 hours a day for an entire year. That is the scale of our annual emissions. And yet, remarkably, only about half of that carbon remains in the atmosphere. The other half, approximately 18 to 20 gigatons per year, is absorbed. This absorption is not the work of human technology or carbon capture facilities, but of living systems of biology itself, working quietly on a planetary scale. The planet's great tropical rainforests in the Amazon, Central Africa, and Southeast Asia together form the largest land-based carbon sink on Earth. They draw in carbon dioxide, much like our lungs draw in air, sequestering it in wood, soil, and roots. The oceans perform a similar function through a combination of chemistry and the actions of microscopic life near the surface. These systems collectively create a kind of invisible infrastructure, an atmospheric safety net that has been quietly absorbing roughly half of all our emissions, year after year, for decades. Without this natural service, the concentration of atmospheric carbon dioxide would be climbing at nearly twice its current rate. the climate projections that are already a source of concern would look dramatically worse. This brings us to a truth about El Niño that the typical weather coverage rarely explores. An El Niño event is not simply a redistribution of heat across the globe. When that vast pool of warm water migrates across the Central Pacific, it does more than just alter patterns of rainfall and drought. Its influence reaches deep into the biology of entire continents. It places immense stress on forests, dries out carbon-rich peatlands, and can push entire ecosystems past the threshold where they absorb carbon and into a state where they begin to release it. The most powerful El Niño events don't just affect the weather, they can temporarily switch off the planet's carbon sink. In the 1997 to 1998 event, for instance, the Indonesian peat fires released an estimated 0.8 to 2.5 gigatons of carbon in a matter of months. This immense emission came from a single geographic region, triggered by a single mechanism. Later, during the 2015 to 2016 event, the most comprehensively observed El Niño in history, the global carbon sink weakened so dramatically that it led to the fastest rate of atmospheric carbon dioxide growth ever recorded at that time. An excess of 2.5 gigatons of carbon was released in a single year. These past events serve as a stark reminder of the system's vulnerability. After both of those episodes, the system eventually recovered. The forests and oceans came back online, resuming their role as carbon absorbers. The growth rate of atmospheric carbon dioxide returned toward its baseline trend, and the scientific community largely filed the events away as significant, but ultimately temporary, disruptions. But this history of recovery now raises a far more urgent question. A question that a handful of researchers are beginning to pose in scientific papers and conference presentations, often in careful, guarded language, is whether that recovery will happen again after 2026. The core issue is not whether the next El Niño will be strong, or whether the droughts will be severe. The fundamental question is whether the carbon sink, after absorbing decades of accumulated damage, will come back online at all. This is the real story. To tell it properly, we must understand why this time is different from all the years that came before. The baseline, the starting condition of the forests, the soils, and the ecosystems that constitute this invisible infrastructure has shifted. These systems are now more degraded, making a full recovery less certain than it has ever been. The floods will be covered, the droughts will be covered, but the system that truly keeps the planet livable is the carbon system, and it is about to face its most serious stress test in human history. To truly grasp what is at stake, we must start at the beginning, with the forecast itself. But to do so, we need to look beyond the conventional metrics. Most people who follow climate news have heard El Niño strength described in terms of a temperature anomaly, but that single number only tells part of the story. The standard instrument for measuring the intensity of an El Niño is the Oceanic Nino Index, or ONI. This metric tracks how much the surface temperature of the Nino 3.4 region in the Pacific deviates from a 30-year average. If temperatures exceed this baseline by more than 0.5 degrees Celsius for 5 consecutive 3-month periods, an El Niño is declared. A deviation of 1.5 degrees signifies a strong event, while anything surpassing 2 degrees enters the territory of a super El Niño. This is the number that forecasters cite and that generates headlines. However, a smaller community of researchers is focusing on a different metric, the Relative Oceanic Nino Index, or ROI. The distinction between these two indices is not merely technical. It represents a fundamental conceptual shift, one that carries profound implications for how we interpret the potential meaning of an event like the one projected for 2026. The primary issue with the standard ONI lies in its methodology. The baseline it uses for comparison is a 30-year rolling average that is updated each decade. As global warming steadily heats the oceans, This reference point for what is considered normal keeps shifting upward. The Pacific Ocean is, in absolute terms, warmer today than it was in the 1990s or 2000s. It is warmer than it was when the 1997 El Niño set the modern standard for a super event. This means that when we see a temperature anomaly for 2026 that appears similar to 1997, we are measuring that anomaly against an already warmer baseline. The absolute temperature of the ocean's surface, the very thing that governs evaporation, atmospheric patterns, and stress on ecosystems, could therefore be significantly higher in 2026, even if the relative anomaly seems comparable. The ROI is designed to account for this discrepancy. Instead of a sliding window, it employs a fixed, longer-term baseline. The result is that many recent El Niño events appear more intense when measured by the ROI than by the standard ONI. This suggests the ONI may be systematically understating the true severity of modern events in absolute terms. This distinction is vital when considering the planet's carbon sinks. The world's forests, soils, and natural ecosystems do not respond to statistical anomalies. They respond to absolute physical conditions. A tree in the Amazon does not register whether a drought is 2 degrees above a 30-year average or 3 degrees above a 20-year average. It only knows the searing heat it feels, the dryness of the soil at its roots, and whether it has enough water to photosynthesize or must shut down to survive. As the background temperature of the entire system rises, each new El Niño strikes a forest that is already more heat-stressed and more vulnerable to collapse. Embedded within this is a quiet controversy that has yet to fully enter the mainstream climate discussion. When we examine the ONI forecast for 2026 and place it alongside the data from 1997, we may be comforting ourselves with a number that is subtly deceptive. We could be observing a relative temperature change and concluding the events are alike, while the absolute temperature regime, the one in which the forest actually exists, is dangerously hotter. When a baseline shifts, every living system that depends on it is forced to shift as well, often toward a breaking point. The climate system is not a single entity governed by one switch. It is a vast, interconnected network. The Pacific Ocean does not act in isolation. When multiple components of this global network synchronize and push in the same direction, the consequences can be far more extreme than any single element would suggest. This brings us to the multi-basin configuration. Climate historians have pinpointed a particular alignment of ocean basins that has coincided with some of the most devastating climate disruptions of the last 150 years. This dangerous configuration amplifies drought stress across the tropical land masses, home to the majority of the world's remaining rainforests. It requires 3 conditions to occur simultaneously: an El Niño in the Pacific, exceptionally warm waters in the Atlantic, and a positive Indian Ocean dipole, where the western Indian Ocean becomes warmer than the eastern side. The last time all 3 of these phenomena clearly aligned was from 2015 to 2016. To find the previous instance, one must go back to the 1870s, a period that climate historian Mike Davis identified as the catalyst for the Great Victorian Famines. That multi-year, multi-continental disruption led to the deaths of an estimated 30 to 60 million people across Asia, Africa, and Latin America, primarily from crop failures caused by concurrent droughts. The 1877 to 1878 El Niño is remembered as one of the most destructive climate events in recorded history, not for its sheer magnitude, but for its devastating configuration across multiple ocean basins. The early signals for 2026 suggest a pattern that bears a troubling resemblance to this historical setup. The Atlantic is already running warmer than average, and preliminary data indicates a warming trend in the Indian Ocean. Layered on top of this, is a factor that was not present in 1877 and was only beginning to be understood as a major scientific concern in 2015. The weakening of the Atlantic Meridional Overturning Circulation, or AMOC. This large-scale ocean conveyor belt normally transports heat away from the tropics toward the North Atlantic. As this circulation slows, heat that would typically be exported toward the pole instead remains trapped in the tropical Atlantic, adding another layer of warmth to the entire system. What does this convergence mean for the global carbon story? It means that the forests most critical to the planet's carbon sink are facing a simultaneous assault from multiple directions. The Amazon, which is sensitive to both Atlantic and Pacific conditions, is hit by El Niño-driven drought from the west and intensified drying from a warm Atlantic to the east. Meanwhile, the forests of Indonesia are squeezed between the effects of El Niño on one side and a positive Indian Ocean dipole on the other. When these powerful systems align, the stress on the forests is not merely additive, it becomes multiplicative. This is not one system failing, but multiple systems coordinating their destructive power against the same target. That target, the global carbon sink, is the one mechanism the planet relies on to absorb our emissions and slow the pace of warming. The multi-basin configuration, therefore, is not a footnote. It is one of the central reasons why 2026 cannot be assessed by simply looking at a Pacific anomaly, and it underscores the profound vulnerability of the systems that keep our world in balance. An interesting thought experiment reveals a telling pattern in our public conversation. If you were to search for El Niño 2026 across major news platforms and review the initial articles, you would find a consistent theme. The overwhelming focus is on the immediate severity of the event, its peak temperature anomalies, its comparison to past super El Niños, and the probability of its onset. But a different, perhaps more critical question is almost never posed. What happens afterward? The number of articles exploring the long-term recovery will likely be near zero, and there is a clear reason for this omission. The acute impacts of an El Niño are dramatic and tangible. Its peak intensity brings floods, droughts, and heat waves that happen on a timescale perfectly suited to news cycles. We see stories of Peruvian farmers whose crops have failed, Indonesian villages shrouded in smoke, and Australian reservoirs running critically low. These narratives have faces, powerful images, and a direct causal line from the climate event to the human consequence. The global carbon cycle, however, operates on an entirely different principle. The fallout from a failing carbon sink is not so easily captured. Its consequences are dispersed across decades, across continents, and even across generations. The surplus carbon dioxide that floods the atmosphere during a major El Niño does not trigger a specific flood the following week. Instead, it subtly alters the very baseline of our climate system. This shift compounds with all other ongoing changes, making each subsequent extreme event slightly more likely, every recovery a little slower, and every climatic tipping point a fraction closer. The effects are profoundly real, yet they remain invisible on the timescale of a news report, which may explain their near-total absence from the public dialogue surrounding 2026. This oversight matters deeply, because the question of recovery is not merely an academic curiosity. It is arguably one of the most vital questions in climate science today. The climate projections that scientists release, already alarming, are built upon a crucial assumption that the planet's carbon sinks will continue to function. These models presume that our forests and oceans will go on absorbing roughly half of all human emissions in the coming decades. While the models do incorporate some gradual degradation of these sinks over time, reflecting current scientific understanding, they do not, for the most part, factor in a sudden, near-term partial collapse. They do not simulate a scenario where the 2026 El Niño damages the tropical forest carbon sink so severely that its recovery is either incomplete or significantly delayed. This is the key detail to remember from the events of 1997 and 2015. In both of those prior instances, the system demonstrated a remarkable resilience. After the 1997 event, the growth rate of atmospheric carbon dioxide remained elevated for about a year before returning toward its previous trend line. A similar pattern unfolded following the 2015 to 2016 El Niño. The anomalous spike in the growth rate eventually subsided. As the rains returned, forests in most regions began to regrow, and the models of the carbon cycle were updated to incorporate what had been learned. Both episodes were ultimately classified as serious but temporary disruptions, stress tests that the planetary system had successfully absorbed and recovered from. This history of recovery has, perhaps, given us a false sense of security. The profound uncertainty that looms over 2026 is not about the stress test itself, but about the underlying condition of the system being tested. The real question is whether our planet has accumulated so much background damage from deforestation, soil moisture deficits, persistent warming, and the incremental decay of its own structural integrity that the recovery we have come to expect may not happen as completely, or perhaps may not happen at all. A temporary shutdown of the carbon sink is a serious problem. A permanent, or even a significantly prolonged one, belongs to an entirely different category of crisis. It is the crucial difference between a sound bridge bearing a designed load and a neglected one facing that same pressure after years of decay. The load has not changed, but the bridge has. To grasp why 2026 could be the event that truly tests this distinction, we must journey back to the last two times the system faltered. Those failures were anything but clean, and they left scars that remain with us today. Before 1997, the scientific community understood, in theory, that El Niño events could disrupt the global carbon cycle. The logic was straightforward. El Niño triggers drought in tropical regions, which in turn stresses vegetation. Stressed plants absorb less carbon dioxide, and as a result, atmospheric CO2 levels grow more rapidly during El Niño years. This was the accepted framework. It was more or less integrated into models and was viewed as a manageable perturbation, a temporary wobble in an otherwise stable and resilient global system. This was the prevailing scientific wisdom, one that saw the Earth as fundamentally robust. Then, in late 1997, the fires began. As flames swept across Borneo and Sumatra, the scientific community witnessed something for which no model had adequately prepared them. The issue was peat. Peat is nothing like ordinary soil, nor is it like the leaf litter on a forest floor or the decaying organic matter that cycles through the carbon system over years or decades. Peat represents carbon that has been accumulating for thousands of years, locked away in permanently waterlogged conditions. In this environment, dead plant material cannot fully decompose. Instead, it simply compresses, compacting layer upon layer over millennia. To understand the gravity of this, one must appreciate that peat is not simply soil. In the waterlogged forests of equatorial Asia, the peat deposits of Borneo and Sumatra can reach depths of 12 to 15 meters. Some of the carbon sealed within these layers has been there since the last ice age. It is not a component of the contemporary carbon cycle. It is more akin to a geological storage vault holding ancient carbon that nature painstakingly removed from the atmosphere over eons. When the severe El Niño drought of 1997 desiccated these peatlands, it created the conditions for something far more sinister than surface fires. It enabled fires to burn underground. Once sufficiently dry, peat burns not just on the surface but deep beneath it, smoldering through the compressed organic layers much like a lit cigarette. This process is slow, persistent, and almost entirely immune to rainfall. A peat fire can continue its subterranean burn straight through a monsoon season, lingering for weeks or months after any visible surface flames have been extinguished. And as it burns, it releases carbon that was never part of the active cycle carbon that had been safely sequestered for centuries. The estimates of what truly burned in 1997 and 1998 vary considerably from one study to another, a fact that itself signals how poorly the event was understood at the time. The most careful analyses place the total carbon released from Indonesian peat fires during that period somewhere between 0.8 and 2.5 gigatons. The sheer range of these figures highlights the scientific shock of the event. As researchers grappled with a phenomenon that had reset their understanding of the planet's vulnerabilities, the sheer scale of the uncertainty is revealing, spanning a threefold difference in estimates. Yet even the most conservative calculations are staggering. At a time when global fossil fuel emissions were around 6.5 to 7 gigatons of carbon per year, the Indonesian fires unleashed a torrent. Over just a few months, from a single archipelago, these blazes released an amount of carbon equivalent to between 12 and 38% of the entire world's yearly fossil fuel output. This was not merely a forest fire. The carbon was erupting from deep within the earth, from peat deposits that had been accumulating for millennia. The immediate consequences were terrifyingly visible. A thick haze smothered Malaysia, Singapore, and vast areas of Indonesia for months. It shut down airports, closed schools, and caused hospital admissions for respiratory illnesses to surge. But while the human health impact was direct and undeniable, the carbon impact was of a different nature, invisible, diffuse, and spread across the entire atmosphere, creating not a local problem, but a global one. The most crucial aspect of the 1997 event is that, according to the understanding of the time, it should have been impossible. The peatlands were not meant to burn. The hydrological systems that kept these landscapes waterlogged were believed to be resilient enough to endure even a severe drought brought on by El Niño. Consequently, the immense store of carbon locked within these deposits was considered, for all practical purposes, permanently removed from the atmosphere. The event shattered these assumptions, exposing a vulnerability in the global carbon system that no one had quantitatively grasped before. It was a profound lesson, and as it would turn out, 1997 was only the first demonstration of this newfound fragility. In the years between 1997 and 2015, a remarkable transformation occurred within climate science. The tools available to researchers became dramatically more powerful. With the launch of the Orbiting Carbon Observatory 2, or OCO2, in 2014, scientists gained their first satellite, capable of mapping atmospheric carbon dioxide with enough precision and resolution to actually see where it was coming from and going on a regional scale. It was a revolutionary new perspective on our planet's metabolism. When the 2015 to 2016 El Niño arrived, it unfolded within the most well-observed climate system in history. Scientists could now watch the global carbon cycle respond in near real time, a feat that was simply impossible in 1997. What the new instruments revealed was a surprise. The headline finding, published in the journal Science Times in 2017, was that the global land carbon sink had weakened by approximately 2.5 gigatons of carbon relative to its expected value during that year. This weakening contributed to the atmospheric growth rate of carbon dioxide hitting 3.05 parts per million in 2016, the largest annual increase ever recorded at that point. While that record has since been approached, in 2016, it sent a genuine shock through the scientific community. But the most interesting discovery was not the total number. The real revelation lay in the geographic breakdown of how and where this systemic failure occurred. In Indonesia and the wider Southeast Asian region, the story was a familiar echo of 1997. Peat fires, once again triggered by an El Niño-induced drought, were releasing ancient carbon from the same compressed peatland deposits that had burned nearly 2 decades earlier. This part of the story, at least, was understandable. It was the very mechanism that the 1997 event had first revealed, now playing out once more across the same vulnerable territory. It was a known threat, re-emerging with devastating consequences. In the Amazon, however, something entirely different was happening. The drought of 2015 and 2016 caused a widespread reduction in photosynthesis across the basin, meaning the forests were absorbing far less carbon than normal. This was not because they were burning, but because intense drought stress was forcing the trees to close their stomata. This act of self-preservation reduces gas exchange and slows the fundamental biological process that drives carbon absorption. In a bad drought year, the Amazon does not simply stop growing, it can begin to reverse its role. While living trees continue to respire, releasing carbon dioxide as a metabolic byproduct, the halt in photosynthesis tips the net balance from absorption to emission. A forest does not have to burn to become a carbon source. It just has to stop functioning normally. And then there was tropical Africa, which presented the most unexpected finding of all. The OCO2 data revealed a large positive carbon anomaly stretching across the central and eastern parts of the continent. This was not driven primarily by fire, nor by a drought-induced shutdown of photosynthesis. Instead, it was caused by increased ecosystem respiration in warm soils. Higher temperatures accelerate the rate at which soil microbes decompose organic matter, releasing carbon dioxide as a byproduct. In essence, the entire tropical ecosystem in Africa, responding to the elevated temperatures of the El Niño period, had sped up its metabolic rate, exhaling more carbon dioxide without any dramatic, visible disruption. The picture that emerged was one of 3 different continents, each experiencing 3 completely different mechanisms of failure. In Indonesia, it was fire. In the Amazon, a shutdown of photosynthesis. And in Africa, an acceleration of soil respiration. All of these were happening simultaneously, all driven by the same global El Niño event, yet operating through entirely distinct pathways. The system had not failed in one predictable way. It had failed in multiple, independent ways all at once, raising profound questions about its overall resilience. Before 2015, climate models had largely been built around the expectation that fire was the primary way El Niño would damage the global carbon sink, an assumption heavily supported by the Indonesian fires of 1997. But the 2015 event revealed that fire is not even necessarily the dominant mechanism. It showed that you can lose the carbon sink without a single visible flame through the subtle physiology of trees under stress and the hidden biochemistry of warming soils. The system, it turned out, has multiple pathways to failure, not just one. And when a strong enough event hits a planet already on a warmer baseline, all of those pathways can fail at the same time. This leads to a common narrative about the 1997 and 2015 events that is slightly wrong, or at least incomplete. The story usually goes that El Niño arrives, the carbon sink weakens dramatically. Atmospheric carbon dioxide spikes, then El Niño ends, the sink recovers, and the growth rate returns to normal. This narrative is not exactly false. The growth rate of CO2 did indeed come back down after both events. The forests did begin to regreen as the rains returned. But if you look more carefully at the numbers, a different and more troubling picture begins to emerge, one that questions the very idea of a full recovery. If you plot the year-over-year growth rate of atmospheric carbon dioxide from the Mauna Loa Observatory, the gold standard for such measurements, running continuously since 1958, You can see this story written in the data. There are clear, sharp spikes in 1998 and again in 2016, corresponding perfectly to those two super El Niño events. They stand out on the graph as moments of extreme planetary stress. But what happens in the aftermath of these spikes is where the real story lies, hinting that the system may not be returning to the same state it was in before. Following the spike of 1998, the growth rate of atmospheric carbon dioxide eventually fell. After the 2016 spike, a similar recovery appeared to take place, but a closer look at the data reveals a more subtle and unsettling trend. The underlying baseline, the rate of CO2 increase in years without an El Niño, has been steadily climbing through the 1990s, the 2000s, and the 2010s. This means that a normal year today sees a faster rise in atmospheric carbon than a normal year did 2 decades ago. While some of this is due to the simple increase in human fossil fuel emissions over that time, separating this human signal from the biosphere's own response is a profound challenge. Some researchers now argue that rising emissions alone do not fully account for this accelerating baseline. There may be a biological component at play, a slow, incremental weakening of the planet's carbon sinks, suggesting that ecosystems are not fully bouncing back after each major disturbance. This idea has been termed the ratchet effect. The ratchet effect theory proposes that each major El Niño event acts as a profound stressor on the world's forests. While these ecosystems do recover, the recovery may not be complete. They return slightly weaker, a little less resilient, and more vulnerable to the next disturbance. The atmospheric CO2 growth rate spikes during the event and drops afterward, but it may not fall all the way back to its previous level. Instead, the baseline ratchets upward, one small increment at a time. This raises a critical question. Does each subsequent super event arrive to find a global system that has fractionally less reserve capacity than the one before? A 2020 study by Hubo and colleagues, published in the journal Times Nature, provided compelling evidence for this narrative, at least within the Amazon. By analyzing decades of data from over 300 permanent monitoring plots, the study revealed a startling trend. The research demonstrated that the Amazon's net uptake of carbon has been in decline since the 1990s. This wasn't simply because more trees were dying. The cause was twofold. The growth rate of surviving trees was slowing down, likely a response to increasing temperature stress, while at the same time, mortality was increasing from drought and wind events. In the dataset of that study, the Amazon had not yet become a net source of carbon overall, but it was clearly trending in that direction. Its reserve capacity, its fundamental ability to absorb carbon beyond its own metabolic needs, was shrinking. This single finding is what lends the 2026 forecast a completely different quality of concern than the events of 1997 or 2015. The system may no longer be returning to the same stable baseline after each shock. What this suggests is that each event may be leaving behind a slightly smaller buffer, a more vulnerable system with a reduced capacity to absorb the next impact. If this is true, then any attempt to predict the recovery after 2026 by simply looking at what happened after 1997 and 2015 becomes deeply flawed. The system those earlier events were recovering from was not the same as the system that the 2026 event is about to encounter. There is a hidden pattern in the timing of these events, one that becomes more apparent the longer we observe it, and it is far from comforting. The Super El Niño of 1997 to 1998 was followed by a gap of roughly 18 years before the next super event in 2015 to 2016. While not a long time in the grand scheme of forest ecology, 18 years is a meaningful period. It was long enough for many of the fire-damaged areas in Indonesia and the Amazon to undergo significant regrowth, for soil moisture deficits to be replenished over multiple wet seasons, and for the slow work of forest recovery to make genuine progress. In other words, the system had an 1-8-year window to rebuild before it was struck again. In contrast, the 2015 to 2016 event is expected to be followed by the 2026 Super El Niño after a gap of only 11 years. This is a dramatically shorter window for recovery. That's just 11 years for Indonesian peatlands, many of which burned in 1997 and then again in 2015, to heal. It's 11 years for drought-stressed trees in the Amazon to rebuild their crucial water reserves and restore their normal photosynthetic functions. And it's 11 years for the soils across tropical Africa to cool and stabilize. Critically, this shortened recovery period is not occurring in a stable environment. These ecosystems are simultaneously being subjected to ongoing background warming, relentless deforestation pressure in the Amazon and Indonesia, and an increased frequency of droughts even in non-El Niño years. This dynamic can be understood through the concept of recovery time versus disturbance frequency. Ecosystems possess characteristic timescales over which they can recover from severe disturbances. A tropical forest subjected to a major drought may need not just months, but potentially years or even decades to fully restore its function as a carbon sink. The soil carbon that burned away in Indonesia in 1997, for example, has not been replaced. That carbon took thousands of years to accumulate, and it would take thousands more to form again if the conditions for peat formation ever return. The recovery of the structural carbon sink the intact peat, the old-growth forest, is simply not happening on the timescale between these events. This is where the story becomes predictive. Modeling studies, such as those by researcher Wenju Kai, have shown that the frequency of Super El Niño events is likely to increase as global temperatures rise. The atmospheric conditions that favor their development, a warmer Pacific Ocean and more energetic tropics, are precisely the conditions that our changing climate is creating. The implication is not just that the events themselves are getting stronger. It is that they are also getting closer together. The recovery windows are shrinking. There is a concept in ecology known as the intermediate disturbance hypothesis, which provides a useful framework for understanding this process. The hypothesis suggests that moderate, regular disturbances can actually increase an ecosystem's diversity and resilience. However, when the disturbance intensity and frequency become too high, the opposite effect takes over. The system no longer has time to adapt. It simply degrades as stress accumulates faster than recovery can occur. One can think of it as the difference between exercise and injury. Moderate stress, followed by adequate recovery, makes a system stronger. But too much stress, too frequently, without enough time to heal, breaks it down. The tropical carbon sink was exercised hard twice in the last 3 decades. It is about to be exercised again, but this time harder, with less recovery time, on a warmer baseline, and in a system with measurably degraded integrity in its most critical regions. The event of 2026 is shaping up to be the first major test where the recovery window may have genuinely run out. And yet, recent findings suggest the situation may be even more advanced than this framework implies. In 2021, a group of Brazilian and international researchers published a paper in the journal Times Nature, Times that quietly but profoundly changed the framing of the entire Amazon carbon debate. Their work suggested that, in a very real sense, the Amazon has already partially flipped. A study led by Luciana Gatti used a deceptively straightforward method to assess the health of the Amazon. Aircraft flew over 4 distinct regions, measuring atmospheric concentrations of carbon dioxide and carbon monoxide. By comparing the air flowing into the forest with the air flowing out, they could determine if a region was a net absorber or emitter of carbon. The technique was, in essence, a way to measure the breadth of the forest on a massive scale. The results from the southeastern Amazon were both unambiguous and deeply alarming. This single region, a forested expanse comparable in size to Western Europe, was found to be a consistent net source of carbon. This wasn't an anomaly tied to an El Niño or a specific drought. Even in normal years, this part of the rainforest had permanently crossed the line from a carbon sink to a carbon emitter. The tipping point, it seems, had already been passed. What could be driving such a fundamental shift? While forest fires contribute, the primary mechanism is a more subtle disruption of the water cycle, driven by deforestation. The Amazon rainforest is remarkable in that it generates its own rainfall through evapotranspiration, as trees draw water from the soil and release it as vapor through their leaves. The forest, in a very real sense, creates the moisture that sustains it. When a critical number of trees are removed, this delicate cycle breaks down. Rainfall diminishes, and the remaining forest grows drier, placing it under increasing drought stress. Trees that once absorbed carbon dioxide now struggle, eventually exhaling more carbon than they inhale. This creates a dangerous feedback loop, as a smaller forest means less recycled moisture, which deepens the drought and accelerates the decline. The situation in the southeastern Amazon appears to confirm a long-held warning from researchers Thomas Lovejoy and Carlos Noe. For years, they have argued that the Amazon has a critical tipping point, estimated between 20 to 25% total deforestation. Beyond this threshold, they predicted the forest's moisture recycling system would break down, triggering a self-perpetuating shift toward a drier, savanna-like ecosystem. This raises an urgent question. How close is the entire basin to this point? Current estimates, which vary by measurement method, place total deforestation at around 17 to 20% of the original forest. The southeastern Amazon, having suffered heavier deforestation and more intense drought, seems to be a grim leading indicator, offering a localized preview of where the entire system may be headed. This altered reality fundamentally changes the risk profile for the next major El Niño, anticipated around 2026. That event will not impact an intact Amazon that is uniformly acting as a carbon sink. It will arrive in a system where one of its four major quadrants is already, under normal conditions, releasing more carbon than it absorbs. The concern is no longer about what it would take to flip that southeastern region. It has already flipped. The critical question is whether the remaining three quadrants can withstand the stress, or if the drought will expand the already failed region and push additional areas past the same threshold. This is a profoundly different scenario than what existed in 1997 or 2015. In those years, the Amazon was stressed from a functional baseline, as deforestation had not yet caused regional sink failure. This time, the stress event will begin with part of the system already in failure mode. Half a world away, in Indonesia, another climate threat known as the peak time bomb has become even more volatile. The 1,997 fires that raged through the peatlands of Borneo and Sumatra took the global scientific community by surprise. These ecosystems had been largely invisible in global carbon accounting. Their immense carbon stocks were underappreciated, and their vulnerability to fire and drought was completely unforeseen on the scale that occurred. In the years following 1997, and again after the fires returned in 2015, significant international efforts were made to address the problem. Indonesia established a peatland restoration agency, and international funds were directed toward re-wetting projects. These initiatives aimed to block drainage canals to raise the water table and suppress fire ignition. Monitoring and fire suppression capabilities were also enhanced. Yet despite these measures, the results have been mixed, and in a crucial structural sense. The situation today is worse than in 1997. The reason for this worsening situation is that the fundamental problem is not the fires themselves, but the drainage that enables them. Beginning in the 1980s and accelerating through the following decades, vast expanses of peat swamp forest in Borneo and Sumatra were systematically drained for agriculture. This network of canals lowered the water table, drying out the upper layers of organic matter and rendering them highly combustible. The fires are merely a consequence of this hydrological alteration. Without drainage, the peat remains saturated and will not burn. With drainage, a normal dry season poses a fire risk, and an El Niño-induced dry season guarantees catastrophe. Despite restoration efforts, the vast majority of the drainage network carved into these landscapes remains intact. Re-wetting projects have addressed only a small fraction of the total drained area, leaving the core structural damage, the lowered water tables, and dried carbon layers largely unrepaired. Layered on top of this unresolved structural damage is a new compounding crisis. The land itself is sinking. When peat burns, it is consumed, its carbon released, and the ground level permanently subsides. In parts of Borneo and Sumatra, the land surface has dropped by meters compared to its level before the era of drainage and fire. This subsidence presents a critical challenge, making re-wetting the land far more difficult. The relationship between the groundwater level and the land surface has been irrevocably changed. Lower ground makes it harder to maintain a high water table, creating a terrible irony. Areas that might have been re-wetted to saturation in 1997 may no longer be salvageable, because while the drainage infrastructure remains, the land surface itself has fallen away. The coming El Niño event of 2026 is set to unfold across an Indonesian peatland environment that is already profoundly compromised. This landscape has been subjected to decades of drainage, has been burned on 2 separate occasions, and has only seen partial re-wetting efforts. Compounding this, the entire region rests on a warmer climate baseline, which is trending toward more severe dry seasons. The result is that the potential for ignition is not merely what it was in 1997. It is demonstrably higher. Beneath the surface lies a vast reservoir of ancient carbon, exposed by years of drainage and now dangerously dry. This enormous quantity of carbon, poised for release, remains a critical omission in most near-term climate models, representing a significant gap in our understanding. This brings us to a major unknown in the global climate equation, the Congo Basin. In 1997, these vast forests were barely part of the conversation. While scientists were aware of their existence and immense scale, the fundamental infrastructure needed to monitor Central Africa's carbon cycle was simply not in place. There were no extensive aircraft sampling campaigns, no robust network of atmospheric monitoring stations, and no satellite instruments advanced enough to confidently assign carbon fluxes to specific regions. Everything changed in 2017, with a landmark discovery published in the journal Times Nature. A research team headed by Simon Lewis and Greta Dari of University College London revealed they had identified and quantified the world's largest tropical peatland. It was not in Indonesia, as long presumed, but hidden within the Congo Basin. Spanning an immense 145,000 square kilometers, an area roughly the size of England, this peatland had been almost entirely overlooked in all prior carbon inventories. The amount of carbon locked within it was staggering, an estimated 30 billion tons. To visualize this figure, it is comparable to the total carbon released by 3 years of humanity's current fossil fuel emissions, all contained within a single vast swamp. For now, the Congo Basin's peatlands remain stable. They are waterlogged and intact, not actively burning. Unlike their Southeast Asian counterparts, the hydrological systems that keep them saturated have not been significantly altered by drainage or agriculture. This means they do not currently pose the same immediate fire risk as Indonesia. However, they possess a critical vulnerability to rising temperatures. Data from the OCO2 satellite during the 2015-2016 El Niño revealed a telling signal. The tropical forests of Africa, including the central region, released a large pulse of carbon. This was not caused by fire or a shutdown of photosynthesis due to drought. Instead, it was a result of increased soil respiration. Warmer soils stimulated microbial activity, accelerating the decomposition of organic matter and releasing carbon dioxide at a faster rate. This makes the Congo peatlands a potential blind spot in our projections for 2026. The scientific community lacks the monitoring capacity to fully predict their behavior. They might remain quiet, or they could release a significant amount of carbon through soil respiration if temperatures climb high enough. Without sufficient data, it is impossible to know which outcome is more probable, and this very uncertainty is a crucial element of the overall risk. The years 2023 and 2024 were exceptional by nearly any climate measure, creating a precarious legacy of what could be called a soil moisture debt. In 2023, the global average surface temperature shattered previous records by a margin that astonished even the scientists who track these climate trends. The repercussions in the Amazon were particularly severe, with lasting effects that are often overlooked when discussing the upcoming 2026 El Niño. The region suffered its most intense drought in recorded history in 2023. Rivers receded to unprecedented lows. Near Manaus, the Rio Negro, a major Amazon tributary, fell to levels unseen since record-keeping began. The ecological toll was stark, with dozens of river dolphins discovered dead in evaporating lakes, while indigenous peoples and riverside communities found themselves isolated as their supply routes vanished. The human impact alone was immense. Yet, for the global carbon story, the most significant outcome of the 2023 drought was its effect on the soil. Soil moisture is far more than a simple metric of ground wetness. It functions as a form of ecological memory. During the dry season, Amazonian trees rely on these moisture reserves, drawing on water accumulated during the previous rainy season to sustain their growth and photosynthesis. Trees with deep roots can even tap into water stored several meters underground reserves that accumulate over many wet seasons and are depleted gradually over many dry ones. A drought of sufficient severity, however, drains not only the shallow moisture, but also these deep reserves, which act as a critical buffer against climate fluctuations. Once this deep reservoir is exhausted, it cannot be replenished in a single wet season. Its recovery may require several consecutive years of above-average rainfall. This raises a deeply concerning prospect for 2026, with another drought forecast before these deep reserves can be restored. The forest faces a compounded deficit. The trees will begin the next dry period already below their typical moisture levels, causing them to reach a state of severe stress sooner, remain in it for longer, and suffer greater cumulative damage. The 2023 drought also led to the death of trees, though not in the dramatic way a wildfire does. This mortality was a quiet, creeping process. Weakened by a lack of moisture, trees became vulnerable to bark beetle infestations, fungal infections, and damage from wind. Across large expanses of the forest, this resulted in a measurable increase in excess mortality. While this would not be captured in fire statistics, its impact on the carbon cycle is undeniable, manifesting as more decomposition of deadwood, greater release of carbon from the soil, and a reduction in the forest's overall standing biomass. These dying and dead trees constitute a lasting legacy from the 2023 event. Their decomposition will continue into 2026, contributing a background flow of carbon emissions on top of whatever the new El Niño itself triggers. What this means is that the ecosystem is not entering the 2026 event from a healthy, hydrated, and fully functional baseline. Instead, it is starting from a state of recovery, still processing the after effects of the most severe drought it has ever known. It is facing a new period of stress, while already depleted and bearing the damage from the last one. The situation is much like an athlete attempting to compete just a week after an injury before their body has had a chance to fully heal. their performance is compromised before the race even begins. The immense strain of the coming event could therefore reveal vulnerabilities that might otherwise have been insignificant had the system simply been afforded the time it needed to recover. In the science of complex systems, there is a concept known as a positive feedback loop. The term is not meant to imply something beneficial, but rather something technical, a cycle that is self-amplifying and self-reinforcing. When a change occurs in one part of a system, it can trigger a change in another part, which in turn feeds back to magnify the original disturbance. This creates more change, which is then amplified further, allowing the loop to propel itself. Our planet's carbon cycle contains several such potential loops, and the concern is that the conditions around 2026 could activate more than one at the same time. The fundamental architecture of the most critical loop is this. Rising atmospheric carbon dioxide warms the climate, which then increases drought stress in tropical regions. These stressed forests absorb less carbon dioxide and, under severe conditions, may even begin to release it. This released carbon adds to the atmospheric concentration, causing more warming, which intensifies the drought, further reducing the forest's ability to absorb carbon. The loop begins to feed itself. Under the stable conditions that have defined most of human history, this cycle did not spiral out of control. The natural carbon sinks were robust enough, the forests resilient enough, and climate fluctuations were temporary enough that the loop would dampen itself rather than amplify. The system would naturally find its way back toward equilibrium. The feedback mechanism was always present, but it was held in check by the buffering capacity of the ecosystem. It raises a profound question. What happens when that natural resilience begins to wear away? What changes when the baseline state of the planet degrades is precisely that buffering capacity. If the ecosystem's ability to absorb and dampen disturbances has been undermined, the feedback loop no longer requires a catastrophically large initial trigger. Instead, a much smaller perturbation can provoke a far larger response. Everything we have seen unfold, from the southeastern Amazon flipping to a carbon source, to the structurally damaged peatlands of Indonesia, to the profound soil moisture deficit of 2023 and 2024. Compounded by background climate warming, all of these factors are eroding the system's resilience. This weakened system is now poised to face a super El Niño event, a shock of immense magnitude. This is what makes the situation genuinely alarming, its inherent non-linearity. Systems governed by positive feedback loops do not degrade in a gradual, linear fashion. They can appear stable for extended periods, giving a false sense of security before suddenly tipping into a completely different state. The transition is not slow, it is a threshold, followed by a rapid and often irreversible shift. The great difficulty with these threshold systems is that it is nearly impossible to determine from the outside how close you are to the edge until after you have already crossed it. The system seems fine, and then, suddenly, it is not. Historically, climate models have struggled to fully capture this kind of non-linearity. This is partly because the processes involved span numerous scientific disciplines: atmospheric physics, forest ecology, soil biogeochemistry, and hydrology. Integrating all of these into a single, cohesive model at a sufficient resolution is both computationally intensive and scientifically incomplete. The models that inform major assessments like the IPCC reports are sophisticated and constantly improving, but they are generally calibrated using the system's past behavior. If the system is about to enter a new regime with no analog in the instrumental record, a model's ability to predict it is, by definition, limited. The best that science can do at this moment is to identify the mechanisms, quantify the individual components, estimate the probabilities of various outcomes, and flag the scenarios that demand our most urgent attention. The year 2026 appears to be flagging a significant number of these mechanisms simultaneously. The tropical forests are not the only buffer standing between human emissions and the full accumulation of carbon dioxide in the atmosphere. The world's oceans also play a monumental role, absorbing approximately 10 gigatons of carbon each year. This amount is roughly equivalent to the uptake of all the planet's forests combined, making the ocean another critical pillar of climate stability. El Niño also influences the ocean's carbon uptake through a mechanism that is distinct from the forest story, but ultimately points in the same troubling direction. Under normal or La Niña conditions, cold, carbon-rich water from the deep ocean upwells to the surface along the equator, especially in the eastern Pacific near South America. As this cold water is exposed to the air, it absorbs both heat and atmospheric carbon dioxide. However, it also releases some of the dissolved carbon it carried up from the depths, making the equatorial Pacific one of the few ocean regions that is a net source of CO2 under normal circumstances. During an El Niño, this process is suppressed as a pool of warm surface water expands eastward, capping the upwelling. Less cold water reaching the surface means less outgassing. In this specific region, the equatorial Pacific actually becomes a weak carbon sink, which might sound like a positive development. But the broader picture across the entire ocean is far more complex. During a super El Niño, vast expanses of the tropical Pacific heat up. Warmer surface temperatures reduce the solubility of carbon dioxide in the water. As a simple matter of physics, warmer water holds less dissolved gas. This effect diminishes the ocean's ability to absorb CO2 from the atmosphere over enormous areas. While the net impact of El Niño on ocean carbon uptake is still debated in scientific literature, several studies conclude that the weakening of the land sink during major El Niño events is the dominant signal, with the ocean's effect being smaller and only partially offsetting. The primary concern for 2026 is that the background warming of the ocean surface, which is now at its highest level in the observational record, has already been reducing the ocean's carbon solubility at a baseline level, independent of El Niño. This means that, if the forest sink weakens significantly during 2026, the ocean cannot be assumed to compensate. It is not a static backup system with limitless capacity. The ocean itself is warming, acidifying, and already showing signs of reduced uptake efficiency. The prospect of losing both of these immense natural buffers at the same time, even partially, is the scenario that pushes climate projections into genuinely uncharted territory. Our models are built on the assumption that at least one of these two major sinks will continue to function at or near its historical capacity. Losing both would represent a fundamental shift in the Earth's system. The story of the failing carbon sinks is deeply intertwined with the human systems that rely on the same delicate climate infrastructure. This connection weaves through our global food system, impacting the agricultural supply chains that nourish billions of people. The very same mechanisms of drought and heat stress that endanger forests also threaten our harvests. It raises a critical question. Is the exposure of our food system to these forces in 2026 a layer of instability that we are failing to adequately address? The answer begins with geography, because here, geography is not a backdrop, but the mechanism of the crisis itself. A super El Niño does not distribute drought at random. It follows predictable patterns dictated by shifts in atmospheric circulation, the same shifts that stress tropical forests. When this drought footprint is overlaid on a map of global agricultural production, the congruence is so striking it demands a closer look. Consider the Mekong Delta, a vast river system that gathers water from parts of China, Myanmar, Laos, Thailand, and Cambodia before fanning out across southern Vietnam into the South China Sea. This region is one of the most fertile rice-growing areas on Earth, feeding a substantial portion of Southeast Asia. However, during El Niño years, the monsoon rains that sustain the Mekong's flow are suppressed. As river levels fall, salt water from the sea pushes deeper inland, contaminating the delta's vital irrigation channels. The consequence is a sharp decline in rice yields. This is not a theoretical risk. During the 2015 to 2016 event, Vietnamese farmers in the delta endured the most severe drought in nearly a century, causing rice production to plummet across the region. A similar pattern unfolds in northern Australia, a major producer of wheat and other grains, a significant amount of which is destined for export. El Niño consistently brings arid conditions to northern and eastern Australia, diminishing rainfall during crucial growing seasons. The event of 1997 to 1999 was linked to a severe drought that affected large swaths of eastern Australia, and the 2015 to 2016 event proved similarly destructive. In these years, the Australian wheat harvest can fall by 20 to 40% in the affected regions. Because Australia is a key global wheat exporter, these shortfalls send ripples through international markets. The vulnerability becomes even more direct and personal in southern Africa. Across Zimbabwe, Zambia, Mozambique, and parts of South Africa, maize is the foundation of the local diet for hundreds of millions. It is not a simple commodity crop as wheat is in Australia. It is the food people depend on for daily survival. El Niño suppresses the summer rains essential for the growing season, and in severe instances, this can lead to several consecutive seasons of below-average rainfall. The 1991 to 1992 El Niño, for example, triggered a drought so severe that it brought famine conditions to Zimbabwe, Zambia, and Mozambique simultaneously. Likewise, the 2015 to 2016 event resulted in widespread crop failures, prompting emergency food assistance declarations across multiple countries at once. In India, the connection between El Niño and the summer monsoon has been documented for more than a century. This seasonal rainfall is the lifeblood for over half of the nation's agricultural land. A strong El Niño disrupts the temperature gradient between the Indian Ocean and the Asian landmass, weakening the circulation that drives the monsoon. The onset of the rains is often delayed, and total rainfall is below average. This shortfall disproportionately harms small-scale farmers who rely on rain-fed agriculture and lack access to irrigation. While India's wheat and rice belts have some protection from irrigation infrastructure, this buffer is not absolute. In a super El Niño year, the climatic stress can be intense enough to overwhelm these defenses in the hardest-hit areas. Then there is northeastern Brazil, in the semi-arid region known as the Sertão. Here, small-scale subsistence farmers are entirely dependent on seasonal rains that El Niño is known to suppress. The region's history is marked by catastrophic droughts during El Niño years, a pattern stretching back centuries. The 1877 event produced a drought that is estimated to have killed between 500,000 and 1 million people. While modern Brazil possesses far superior infrastructure and social safety nets than it did in 1877, the Sertão remains one of the most climate-vulnerable agricultural zones in the Americas. A super El Niño is the specific historical trigger for its most devastating outcomes. This is the point where these regional agricultural risks converge into a global crisis. The threat of simultaneous, multi-regional crop stress in 2026 presents a challenge fundamentally different from any single regional failure due to the very architecture of the global food system. Modern agricultural supply chains are integrated on a worldwide scale, a design that delivers remarkable efficiency in normal conditions but reveals a remarkable fragility in abnormal ones. When Brazil experiences a poor maize harvest, global markets can adjust. When Australia has a poor wheat year, the system adapts. When India faces a monsoon shortfall, global rice markets compensate. In isolation, Any one of these adjustments is manageable. The global system contains enough reserve capacity and geographic diversity of supply to absorb failures in a single region. What the system cannot easily withstand, however, are simultaneous failures across multiple major producing regions at the same time. This is the precise scenario a super El Niño creates, not by causing a single catastrophic failure, but by forcing multiple regions to underperform concurrently. This drains the reserve capacity of the global food system from many directions at once. Global grain stocks, the buffer that smooths out production variability from year to year, are drawn down faster than they can be replenished. As a result, prices rise. Import-dependent countries, many of them among the world's poorest, face severe food security stress, not because their own harvests failed, but because the global price of food has soared beyond their citizens' reach. Layered on top of this is a fragility unique to modern industrial agriculture, one that makes the scenario in 2026 structurally different from past food crises, like the one in 1973 to 1974. Today's high-yield agriculture is fundamentally dependent on nitrogen fertilizer. The Haber-Bosch process, the industrial chemistry that transforms atmospheric nitrogen into the ammonia used in fertilizer, is credited with feeding approximately half of the current global population. This reliance introduces a vulnerability that is entirely modern, a dependency that underpins our ability to feed the world, yet also exposes it to unprecedented risk. Without the aid of synthetic nitrogen fertilizer, the agricultural lands of our world would be incapable of producing enough food to support a population of 8 billion people at today's dietary levels. The creation of this essential compound relies on the Haber-Bosch process, a method that is fundamentally dependent on natural gas. This process is intensive in its use of both energy and feedstock, creating a direct and sensitive connection between the energy market and the global food supply. This linkage means that the price and availability of natural gas can immediately impact the cost of food. This vulnerability becomes most acute in years of high crop stress, which are precisely the times when farmers most need to maximize their yields through heavy fertilizer use. If, during such a period, natural gas prices are also high due to geopolitical tensions, infrastructure limitations, or competing demands from heating and power generation, fertilizer costs can soar. This creates a cruel paradox, where the tool farmers need most becomes least affordable at the moment of greatest need. This is not merely a hypothetical risk. It became a stark reality in 2021 and 2022, when spikes in natural gas prices, following disruptions in European energy markets, pushed fertilizer costs to historic highs. As a result, farmers in numerous developing nations were forced to reduce their application rates, leading to diminished yields that had repercussions across several growing seasons. Looking toward the year 2026, forecasts of an arriving El Niño suggest that the demand for fertilizer will peak simultaneously across multiple regions already under stress. The geopolitical climate surrounding energy markets shows no signs of being more stable than it was in 2021. The agricultural supply chains that serve the areas most vulnerable to El Niño-induced drought have not become more resilient. And all the while, the global population that relies on these very supply chains has grown larger. This convergence of factors echoes a past crisis. The emergency of 1973 to 1974, which unsettled governments and created the first modern global food security crisis, was born from a combination of climate stress, an oil shock, and simultaneous crop failures in several regions, all in a world of just 4 billion people. The underlying mechanics in 2026 appear structurally identical: climate pressure, energy market constraints, and widespread agricultural strain. Yet today, our world holds 8 billion people, and our supply chains are far more integrated. This integration brings efficiency in normal times but it also introduces a profound fragility when subjected to simultaneous shocks. This agricultural vulnerability does not alter the fundamental story of the world's carbon sinks, nor does it make the failure of forests more or less probable. Instead, it represents another consequence of the same underlying climate stress, driven by the same El Niño patterns and affecting the very populations who are already most exposed to a warming world. It raises the question of how many different systems can be stressed at once before a wider breakdown occurs. These issues are not separate, they are branches growing from the same tree. And in 2026, that tree may be about to endure a storm of a magnitude it has not seen in generations, on ground that is already far less stable than it appears. There is a particular year that climatologists sometimes refer to with a certain gravity, a year that serves as a benchmark for worst-case scenarios. This is not a year you will find mentioned in press releases or in the summaries of IPCC reports. Instead, it is discussed in the hallways of conferences and used to frame academic papers on compound climate risk. It is invoked when scientists try to define the outer limits of what can happen when multiple systems fail at once. That year is 1877. The reason for this quiet discussion is not any uncertainty in the science. Rather, it is because the scale of what occurred is so immense that it is difficult to describe without sounding deliberately alarmist. But this is not alarmism. It is simply what the historical record shows. Based on the limited instrumental records from the era, the El Niño event of 1877 to 1878 was one of the most powerful of the 19th century. Reconstructions of sea surface temperature anomalies derived from historical proxies like coral records, tree rings, and documentary sources suggest an event of a magnitude comparable to the one in 1997. But the 1877 El Niño did not act in isolation. It emerged within the context of a warm Atlantic and what paleoclimatological data suggests may have been a positive Indian Ocean dipole. This was the same multi-basin alignment of oceanic and atmospheric systems that we have been discussing as a potential feature of the 2026 setup. With multiple ocean basins and atmospheric circulation patterns all pushing in the same direction at the same time, the stage was set for a global catastrophe. The result of this climatic convergence was a series of coincident droughts that spanned 4 continents simultaneously. In India, the country experienced one of the most severe monsoon failures in its recorded history. The drought of 1876 to 1878 devastated crops across the Deccan Plateau, Madras, Bombay, and vast areas of what are now Rajasthan and Uttar Pradesh. In China, a catastrophic drought afflicted the northern provinces of Shaanxi, and Henan regions that were already facing population pressure and had scarce grain reserves. Brazil's Sertão, the semi-arid interior of the northeast, endured the Grande Seca, or the Great Drought, which contemporary accounts described as the worst in living memory, wiping out harvests for multiple consecutive growing seasons, and across large portions of sub-Saharan Africa. The same atmospheric patterns suppressed rainfall in regions that possessed no infrastructure to cope with agricultural failure, lasting several years. The total death toll from what became known as the Great Victorian Famines, the aggregated mortality from the events in India, China, Brazil, and Africa between roughly 1,876 and 1,879, with effects lingering into the early 1880s, is estimated to be somewhere between 30 and 60 million people. The very existence of this wide range is a testament to how difficult it is to count the dead when they are spread across 4 continents. These were not deaths from a single dramatic incident, but from the slow, grinding accumulation of hunger, disease, displacement, and the ultimate collapse of the social structures that normally protect people from subsistence failure. Historian Mike Davis provides the definitive account of these events in his 2001 book, Late Victorian Holocausts. His central argument is a critical one that deserves serious consideration. Davis's thesis posits that these famines were not simply acts of nature. Instead, they were the product of a specific intersection between a climate shock and a political economy. In this case, it was the colonial system, which was structured in a way that actively disabled the normal social responses that would have mitigated a famine. According to Davis's research, colonial economic policy prioritized market functions over food security, leading to grain being exported from famine-stricken regions of India, even as millions starved. Relief efforts were either withheld, delayed, or administered in a manner designed to minimize cost and enforce labor discipline. The railways, a hallmark of colonial infrastructure that could have theoretically transported food to the affected populations, were instead used to move grain toward ports for export. Davis's argument is not that the climate was irrelevant, but that it was a trigger. The true catastrophe unfolded because of a human-made system that amplified the climate shock into a disaster of unimaginable proportions. It forces us to ask whether the disaster was the drought itself or the human response to it. The true story of the Great Victorian Famines is often misunderstood. The climate event, a powerful El Niño, was not the sole cause, but rather the trigger. It was the stressor that exposed the deep structural failings of a political and economic system that showed little real concern for the survival of its people. While the El Niño provided the environmental pressure, it was the colonial system that had systematically dismantled the resilience of local communities. The convergence of these two forces produced a death toll so immense that it permanently reshaped the demographic map of several continents. This history raises a pressing question for our own time, particularly for a year like 2026. Why does this matter now? It is not because we are on the verge of repeating those exact famines. To suggest so would be to ignore the profound changes in our global capabilities. Today, institutions like the World Food Programme and the Food and Agriculture Organization exist to coordinate international efforts. Our global grain reserves, though finite, are vastly larger and more accessible than anything imaginable in 1877. Furthermore, sophisticated early warning systems can now anticipate droughts and crop failures months ahead, allowing for proactive measures rather than reactive responses after mass mortality has begun. A complex international humanitarian architecture is in place, a system that, for all its flaws, is functional and real in a way that simply had no parallel in the 1870s. These are not minor details. They are fundamental differences, and intellectual honesty demands that we acknowledge them rather than using the past merely as a rhetorical tool. But this is where the comparison becomes truly insightful, posing a question that is often overlooked in mainstream discussions about climate risk. The critical question is not whether we will suffer the same kind of famine mortality seen in the Victorian era. Instead, we must ask whether the very structure of our modern global system, its intricate interdependencies, its relentless optimization for efficiency over redundancy, has created entirely new categories of fragility. Have we, in solving the problems of the 19th century, inadvertently engineered new, perhaps even greater vulnerabilities for the 21st? The world of the 19th century was fragile, in a manner characteristic of isolated and poorly connected systems. When a harvest failed in India, for example, each region was largely left to fend for itself. There was little capacity to import food from unaffected areas at the necessary scale or speed. The logistics were simply not there. The political will to prioritize feeding people over generating export revenue was absent, and the financial mechanisms to fund such massive emergency food transfers across continents had not been conceived. This was a fragility born of disconnection. Today, our world is fragile in a completely different way, one defined by hyper-integration. Our systems are tightly coupled, highly optimized, and profoundly interdependent. This means a disruption in one corner of the globe does not remain localized. It propagates throughout the entire network. When a major crop failure in one breadbasket region occurs, it drives up global commodity prices, impacting every import-dependent nation at the same time. When a shock to the energy market disrupts fertilizer supply chains, it doesn't just harm one nation's agricultural output. It raises the cost of farming across multiple continents within a single growing season. And when shipping bottlenecks emerge from simultaneous demand spikes, the nations least able to compete for scarce cargo space are often the very ones most reliant on imports for their food security. The period from 1973 to 1974 offers a sobering historical preview. A combination of a moderate El Niño event, a massive Soviet grain purchase that depleted American reserves, and an oil embargo that caused fertilizer prices to skyrocket, all converged to create a worldwide food price crisis. The US Secretary of Agriculture at the time called it the most serious food situation since the Second World War. It is crucial to remember that this crisis was triggered by a moderate El Niño, not a super event. It did not strike a world already weakened by degraded forests or agricultural systems suffering from pre-existing soil moisture deficits. A moderate climate event, combined with coincidental shocks to supply chains and energy markets, was enough to generate a global food security emergency in a world of just 4 billion people. As we look toward 2026, the world's population has doubled to 8 billion. The agricultural supply chains that feed these 8 billion people are more globally integrated than ever before, making them more efficient under normal conditions, but also more simultaneously exposed during abnormal ones. The energy market dependencies woven into these supply chains are arguably even more complex and geopolitically fraught than they were in 1973. And critically, the El Niño forecast for 2026 is not moderate. The current consensus among modeling ensembles points toward a super event, comparable in strength to the two most powerful ever recorded. So, are we more resilient than the world of 1877? In many of the ways that defined Victorian fragility, the answer is an unambiguous yes. Our humanitarian infrastructure, early warning capabilities, the sheer productive power of modern agriculture, and the institutional frameworks for emergency aid are all genuine, life-saving advances. Yet, a second question looms. Are we also more fragile than in 1877, but in different dimensions? Here, the answer also appears to be yes. In terms of systemic interconnection, dependency on specific inputs, and the optimization of supply chains, we have introduced new vulnerabilities. We have built a system that can fail in ways the disconnected Victorian world simply could not. The scenario where these modern fragilities come to dominate in 2026 is not a distant science fiction fantasy. It sits firmly in the category of a tail risk, an event with a low probability, but an extraordinarily high consequence, and one that is structurally plausible given our understanding of the system's mechanics. Such risks, especially when they concern something as fundamental as the global food supply, deserve to be named clearly and taken seriously. This is not a call for panic, which serves no one. It is a call for preparation. The difference between a managed stress event and an unmanaged, cascading catastrophe is almost always the degree to which we prepare. And preparation can only begin when we first acknowledge that the risk is real. The year 1877 remains a terrible, sobering data point on what happens when climate systems and unprepared human systems collide. We have far more tools for preparation now. The question is whether we have enough. There is a number that does not yet exist, a figure that has not been recorded or confirmed, but one that scientists who study the carbon cycle will be watching with intense focus. Its arrival is anticipated in the latter half of 2026 and into 2027. This number will not command newspaper headlines or be the subject of a major press conference. It will not provoke the immediate, visceral response that a video of a flood or a photograph of a wildfire does. Instead, it will emerge quietly within a dataset, be debated within a scientific paper, and if it lands where worst-case scenarios suggest it might, it will silently alter the fundamental mathematics of our world. That number is a range, 3.5 to 4 parts per million per year, representing the annual growth rate of atmospheric carbon dioxide. To fully appreciate the gravity of that range, one must understand the context it is measured against and the origin of the measurement itself. High on the slopes of a volcano on the Big Island of Hawaii, the Mauna Loa Observatory sits at an elevation of roughly 3,400 meters. It was selected in the 1950s for atmospheric monitoring because of its profound isolation, far from industrial pollution and dense forests, and high enough to sample air that reflects a true global average, rather than any local source or sink. Since 1958, this facility has been continuously recording atmospheric carbon dioxide concentrations. The result is the Keeling curve, named for the scientist Charles David Keeling, who initiated the program. It stands today as the longest, most complete record of atmospheric carbon dioxide in existence. This remarkable record reveals two distinct yet intertwined patterns with startling clarity. The first is the seasonal oscillation of the planet, a rhythmic breathing as carbon dioxide levels fall during the Northern Hemisphere's summer, when plant life flourishes and absorbs more carbon, and rise through its winter as vegetation decays. But riding atop this natural cycle is the second pattern, a steady, long-term upward trend driven by the human combustion of fossil fuels. For 67 years, this trend has climbed without a single interruption. It is a visual testament to a profound and ongoing transformation of our atmosphere. What has changed over those 7 decades is not the direction of the trend, but its velocity. Through the 1960s and 1970s, the annual growth rate of atmospheric carbon dioxide averaged approximately 1 to 1.2 parts per million per year. By the 1980s and 90s, it had climbed toward 1.5 to 1.8. During the 2000s and 2010s, it pushed further, nearing 2.2 to 2.5. In the last decade, the background rate, setting aside the spike years associated with El Niño, has hovered around 2.4 to 2.8 parts per million per year. This acceleration reflects not only the growth of global emissions, but also the incremental weakening of the natural carbon sinks that absorb them. Both forces are pushing the number higher over time. The El Niño spike years are clearly visible in the Keeling curve as temporary deviations from the long-term trend. In 1998, after the peak of the Super El Niño event of 1,997-1,998, the growth rate jumped significantly before settling back toward the baseline in the years that followed. Similarly, in 2016, after the 2015-2016 event, the rate hit 3.05 parts per million, which, at the time, was the highest annual reading ever recorded. But then, it too dropped back. The spike was observable, and so was the recovery. The climate system appeared to absorb the shock and return to its established trajectory. However, in 2023 and 2024, something deeply significant occurred. Even in the absence of a Super El Niño, the growth rates registered at the high end of recent experience, falling somewhere in the 2.8 to 3.2 range, depending on the specific measurement window. This was driven by a confluence of factors: record global temperatures, the 2023 Amazon drought, and the general warming of the entire system. These were not El Niño spike numbers. They were the new normal. The entire trend line had fundamentally shifted upward, setting a far more dangerous stage for what might come next. Now, place the 2026 El Niño forecast on top of this already elevated baseline. The models project a peak of +2 to +2.75 degrees Celsius in the Niño 3.4 region. This is compounded by a multi-basin configuration, adding simultaneous heat stress from the Atlantic and Indian Oceans. The southeastern Amazon is already functioning as a net carbon source even before the event begins. Indonesian peatlands are structurally primed for ignition following decades of drainage and 2 previous fire events. A soil moisture deficit from the 2023 drought still lingers across the wider Amazon basin, and the Congo basin remains a wild card, a region where monitoring infrastructure is insufficient to predict its response. When these inputs are processed through the logic of what occurred in 2015, 2016, but adjusted for far worse starting conditions, a growth rate in the range of 3.5 to 4 parts per million becomes a plausible outcome. This is not the central estimate, nor is it a certainty. The most likely scenario is probably closer to the 3 to 3.5 range, consistent with a severe event on a degraded baseline. But that upper end of plausibility, the scenario where multiple failure mechanisms operate at once from a weaker starting point, reaches into territory never before seen in the 6-7-year history of the Mauna Loa dataset. Let that idea settle for a moment, because it merits more than a passing glance. In 67 years of continuous measurement, spanning the entire era of modern climate science and the industrial-scale burning of fossil fuels, the growth rate of atmospheric carbon dioxide has never reached 3.5 parts per million in a single year. This holds true across every El Niño, every volcanic eruption, and every extreme weather event on record. A reading of 3.5 to 4 inches, 2027, would be genuinely unprecedented. It would sit entirely outside the envelope of everything the observational record has ever shown us. And here is the part that should be more concerning than the number itself. Such a reading would not simply represent a bad year for the carbon budget. It would be a diagnostic signal. It would be a measurement that tells us something specific and vital about the state of the system generating it. This is because the growth rate of atmospheric carbon dioxide is not just an output. It is an indicator of the balance between 2 powerful forces: the amount of carbon humanity emits and the amount the natural world absorbs. If emissions are relatively stable and the global clean energy transition, while insufficient, has at least slowed their growth and the atmospheric growth rate spikes dramatically, the conclusion is inescapable. The spike would be telling us that the absorption side of the equation has weakened, a profoundly worrying sign that the planet's ability to buffer our impact is beginning to falter. The Earth's great carbon sink has faltered. While not a complete or perhaps permanent collapse, the failure is measurable, significant, and conveyed by a number that is impossible to disregard. For the last decade, the global response to climate change has been organized around a central project: the transition to clean energy. This effort has yielded remarkable successes. The deployment of solar power has been genuinely extraordinary, outpacing nearly all predictions made back in 2015. Wind capacity has grown, coal use in developed nations has fallen, and the adoption of electric vehicles has surged. The cost of battery storage has plummeted. These are not small victories. They are the result of immense investment, political will, and technological innovation, leading to real reductions in the rate of carbon dioxide emissions. Yet, a reading of 3.5 to 4 parts per million for atmospheric carbon dioxide growth in a single year, such as 2027, would represent the nullification of a vast portion of those hard-won gains. This does not mean the clean energy infrastructure would vanish. Instead, it suggests that the cumulative carbon benefit from years of effort, every solar panel installed since 2015, every coal plant retired, Every electric vehicle replacing a gasoline-powered one could be overwhelmed in just 12 months. A single year of failing forests and soils, driven by a climate event the system could no longer absorb, would effectively cancel out our progress. This is not an argument against the clean energy transition. Rather, it is a profound argument for understanding what that transition is truly racing against. The standard view of climate policy is a race against our own emissions, a challenge to reduce human carbon output quickly enough to remain within our planet's remaining carbon budget and avoid crossing the 2 degrees Celsius warming threshold. While this framework is correct, it is also incomplete. We are simultaneously in a race against the degradation of the very natural systems that have been our silent partners, absorbing nearly half of all the carbon we emit. These systems are not a fixed, reliable asset. They are a living, stressed, and weakening buffer that has been quietly subsidizing our climate timeline for decades. A reading of 3.5 to 4 parts per million would be the clearest signal yet that this vital subsidy is becoming dangerously unreliable. The carbon budget, the total cumulative emissions the world can still release before likely exceeding 2 degrees of warming, is periodically updated as climate science advances. Current estimates from the IPCC place this remaining budget somewhere between 200 and 300 gigatons of carbon dioxide from 2023 onward. That may sound substantial, but with global emissions currently at roughly 37 gigatons per year, the budget could be exhausted in as little as 5 to 8 years. The margin for error is already incredibly thin. A year where the carbon sink weakens enough to leave an extra 1 to 2 gigatons of carbon in the atmosphere, as implied by a 3.5 to 4 parts per million growth rate, tightens that margin further. It might not be catastrophic in a single year, but the cumulative effect is deeply meaningful. Crucially, the models used to calculate the budget do not currently assume this kind of sink failure. If those models require revision, if the sink is weaker and more vulnerable than we thought, then the policies built upon them must also be revised. The timelines for net zero, the temperature projections, and our assumptions about nature's ability to soften the blow of our emissions all become more urgent. This is the figure to watch. Not because it will tell you that floods are severe or droughts are worsening. The news will cover those events extensively. This number tells a deeper story that the headlines will miss. It reveals whether the planetary system that has been quietly protecting us is still functioning. It is a vital sign for the invisible infrastructure of the Earth's carbon cycle, indicating whether it is holding firm under the greatest stress it has faced in human history. It tells us if the buffer is intact. This number will appear in a routine data update, likely sometime in 2027. It will not trend on social media or lead the news, but it will, in a very real sense, be one of the most important figures ever measured, and the scientists who watch for it already know what they are hoping not to see. The names Thomas Lovejoy and Carlos Nobre command immense respect within tropical ecology. They are not fringe scientists publishing speculative work in obscure journals. On the contrary, they are among the most cited and influential figures in their field, whose research has shaped policy at the highest levels, and whose reputations are built on decades of careful, empirical work. So, when they co-authored a paper in 2018 arguing that the Amazon rainforest may be nearing a point of no return, it was not a provocation. It was a solemn warning from two people who had dedicated their careers to understanding this vital ecosystem. Their paper argued that the Amazon is approaching a critical tipping point. This is a threshold beyond which the interconnected feedbacks between deforestation, reduced rainfall, and forest dieback would become a self-sustaining cycle. Such a cycle would initiate a permanent transition of the world's largest tropical rainforest into an ecosystem resembling the Cerrado, the fire-adapted savanna that borders the Amazon. It would cease to be a forest and would no longer function as a carbon sink. It would become a fundamentally different system, incapable of performing the critical functions the intact Amazon currently provides for the entire global climate. The model, developed by Lovejoy and Nobre, identifies a specific trigger for this collapse: the deforestation of approximately 20 to 25% of the Amazon's original expanse. Below this threshold, the system contains enough intact forest to maintain the moisture recycling process that keeps the interior of the basin wet. But if deforestation crosses that line, the feedback loop could take over. Once initiated, the direction of change would become, for all practical purposes, irreversible on any timescale relevant to human civilization, locking the planet into a new and far more dangerous reality. The total area of the Amazon that has been lost to human activity, cleared, burned, or otherwise degraded, now stands somewhere between 17 and 20% of its original expanse. The exact figure shifts depending on the definition of deforestation, the specific satellite data used for analysis, and whether one includes forests that are still standing but have lost their ecological vitality. This brings the ecosystem perilously close to a critical threshold proposed by scientists Thomas Lovejoy and Carlos Nobre. The margin for error is no longer comfortable. For some parts of the basin, it may not exist at all. In the southeastern Amazon, for instance, the rate of local deforestation is already far greater than the average for the entire basin. This is the very region that a study led by Luciana Gatti, using aircraft to sample the air, identified as having become a net source of carbon even in normal years. For this vast area, the tipping point is not a future possibility. By several key metrics, its own local version of that threshold has already been crossed. To grasp why such a threshold exists, why the Amazon cannot simply shrink indefinitely without triggering a system-wide change, we must first understand a remarkable truth. The rainforest engineers its own weather. This is not a poetic metaphor, but a physical reality, one that has been meticulously measured, modeled, and documented over the last 4 decades. The mechanism behind this feat is transpiration. The forest's trees draw immense volumes of water from the ground through their roots, channeling it up through their vascular systems. This water is then released into the atmosphere as vapor through tiny pores on their leaves, known as stomata. The scale of this process is difficult to comprehend. A single large tree in the Amazon can release hundreds of liters of water each day. When you multiply that effect by the estimated 400 billion trees across the intact Amazon basin, the result is a truly staggering flux of moisture. According to some estimates, the forest releases between 7 and 8 trillion liters of water into the atmosphere every single day through this process of evapotranspiration. This moisture does not simply dissipate. Instead, it rises, cools, and condenses to form clouds. These clouds then release their water as rain, not always directly over the same area, but often carried westward and southward by prevailing atmospheric currents. This means that the trees in the western and southern reaches of the Amazon are, in a very real sense, drinking water that was first transpired by the forests to the east and north. In this elegant continental scale cycle, the forest waters itself. Researchers have given this phenomenon a name that beautifully captures its scale and significance: the flying rivers. These atmospheric currents of moisture, generated by the forest's own biological activity, carry a greater volume of water than the Amazon River itself discharges into the ocean. They are the invisible hydraulic engine that maintains the humidity of the continent's interior, allowing a lush rainforest to thrive where a dry savanna might otherwise exist. But this entire system is profoundly dependent on the very trees that create it, which raises a critical question about its resilience. If you remove a sufficient number of these trees, the flying rivers begin to weaken. This initiates a dangerous self-reinforcing feedback loop. Less evapotranspiration leads to less moisture being recycled into the atmosphere, which in turn means less rainfall over the interior of the basin. The resulting drought conditions place stress on the remaining trees, causing them to transpire less, which further reduces rainfall. The system begins to run in reverse, spiraling toward a drier state. For a time, the ecosystem can absorb these losses, as the remaining forest is vast enough to maintain a sufficient flow of moisture. But there is a limit. This limit is the 20 to 25% deforestation threshold that Lovejoy and Nobre identified. At this point, the remaining forest is no longer large enough to sustain the flying river system at the level required to keep interior rainfall above the minimum needed for rainforest vegetation. Once that threshold is crossed, the negative feedback loop takes over, driving the system toward a new, irreversible state. It is vital to understand what this transition would actually look like, as it defies the common image of a sudden, catastrophic ecosystem collapse. It would not be a single, continent-spanning wall of fire or an abrupt die-off in one season. Instead, the change would likely resemble what is already unfolding in the southeastern Amazon. It would manifest as a series of worsening drought years, an increase in forest mortality, and the spread of fires into areas that were historically too wet to burn. Over time, the moisture-dependent trees of the rainforest would be gradually replaced by fire-adapted grasses and shrubs characteristic of the neighboring Cerrado savanna. The footprint of this degradation would expand incrementally. The boundary between intact and transitioning forest creeping westward and northward, year after year. The process is so gradual that in any single year, it might not register as a catastrophe, but rather as just another bad drought. The insidious nature of such threshold systems is that a transition can be well underway long before the data makes it unmistakable. Eventually, the satellite record would show the evidence. Expanding areas of net carbon release, rising rates of canopy mortality, the appearance of fires in historically moist zones, and shifts in the timing of leaf growth that signal a change in vegetation type. However, the underlying process driving these signals, the breakdown of the flying river system, could become irreversibly committed before these surface indicators provide definitive proof. It is entirely possible that we would only know the tipping point was crossed with certainty after a decade of subsequent data makes the trajectory undeniable. By that point, the fundamental physics of the water cycle would have taken control. Simply halting deforestation at that stage would not be enough to reverse the process. The remaining forest would be too diminished to restore the flying rivers to their former strength. Unable to pull the interior back from the drier equilibrium it is settling into. This is the specific mechanism by which an event like the projected 2026 El Niño could act as a trigger. It is crucial to be precise about what trigger means in this context. It is not a cause in the simple sense, the way a lit match is the cause of a fire. The true cause is the accumulated damage. The 17 to 20% of the original basin already lost, the decades of degraded moisture recycling, the incremental drying from background global warming, and the significant soil moisture deficit the basin still carries from the 2023 drought. All of these factors represent the fuel, patiently waiting for a spark. The 2026 El Niño is poised to add a stress that could push more of the Amazon across a critical local boundary, one already breached in its southeastern region. This would expand the zone of committed transition, potentially driving the basin's vital flying river system past a point of no return, even if all deforestation ceased immediately. It is important to state clearly that the scientific literature does not declare this outcome is certain. While the Lovejoy-Nobre hypothesis is widely respected, it lacks unanimous acceptance, and the precise location of the tipping threshold remains an area of active research and genuine uncertainty. Some models place this point higher than the estimated 20 to 25% deforestation, while others argue the ecosystem has more resilience than the flying river model implies. The debate is scientifically legitimate, but what is not debated is the threshold's existence. The concept of a tipping point in the Amazon's moisture recycling is not seriously contested. The question is where it lies and how close we are. Given that basin-wide deforestation is at 17 to 20% against a threshold of 20 to 25%, and with the 2026 El Niño set to deliver the most severe moisture stress since the satellite era began, the uncertainty is not reassuring. The error bars seem to bracket the danger. We may only recognize the transition has truly begun years after its onset. As the signal builds incrementally in satellite data, slight increases in carbon release, canopy temperature, and fires in wet zones. Each signal could be dismissed as a local anomaly, but the overall pattern may take years to become undeniable. By then, the process driving it could be irreversible. This is the nature of threshold systems, and why Lovejoy and Nobre argued in 2018 that waiting for certainty means waiting too long to act. The fate of the Amazon, however, is not a story that unfolds in isolation. It is part of what is known as a compound tipping corridor, and this is where the narrative becomes genuinely difficult to scope. The challenge arises not because the science is speculative, but because the interactions between the planet's systems are so profoundly complex. Even the researchers who study them most intimately are reluctant to offer confident, quantitative predictions about how such a cascade might unfold. The honest answer to what happens when multiple tipping elements begin to interact is that we do not fully know, but what we do understand is more than enough to compel us to take the question very seriously. The science of tipping points in the Earth system is not a settled field, and any account suggesting otherwise does a disservice to the reader. There is legitimate scientific debate over what exactly constitutes a tipping element, a component of the Earth system that can shift abruptly from one state to another when a forcing crosses a threshold. Researchers actively debate where these thresholds lie, how confident we should be in any particular estimate, and how rapidly a tipped system transitions to its new state. The uncertainty ranges on some of these points are wide, and the models used to estimate them have known limitations. It is natural for reasonable scientists to look at the same data and reach different conclusions about how close specific systems are to their critical points. These disagreements are not a sign of a broken science. They are a sign of a science working at the very frontier of what is currently knowable. Yet within that uncertainty, a body of literature has been growing steadily over the past decade, and it received considerably more attention in the most recent IPCC 6th Assessment Report. This research argues for something beyond just considering individual tipping elements in isolation. The argument is that these elements are not independent of each other. They are connected through physical, chemical, and biological pathways. This interconnectedness means that when one system tips, it does not just matter for that system alone. It loads additional stress onto other systems, shifting their own probability distributions toward their thresholds. The result is what researchers call a tipping cascade or a tipping corridor, a regime in which the destabilization of one system measurably increases the probability of destabilization in others, even if the connections are indirect and the timescales are different. A 2018 paper in the journal Times Proceedings of the National Academy of Sciences, from authors including Will Steffen and Johan Rockström, introduced the concept of hothouse Earth. This was a scenario where a series of tipping elements cascade in sequence, driven by a combination of human forcing and the internal feedbacks between the systems themselves. Such a cascade could push the planet toward a dramatically warmer equilibrium that no amount of emissions reduction could reverse once underway. The paper was controversial when published, criticized by some for overstating the certainty of cascade dynamics and presenting a worst-case scenario without sufficient qualification. Those criticisms have merit. The hothouse Earth scenario is not a prediction, but a risk framing an attempt to characterize the outer boundary of what these coupled system dynamics could produce. Yet the core physical argument that tipping elements are connected and that their connections matter has held up and strengthened in the literature since 2018. To understand this picture more clearly, we can walk through the specific systems that researchers have identified as most relevant to the 2026 story. Each one is in a different state of stress and proximity to its threshold, and together they form a complex web of risk worth understanding. We can start with the Atlantic Meridional Overturning Circulation, the AMOC. This is the large-scale ocean current system that functions as a conveyor belt for heat in the Atlantic Basin. It works by drawing warm surface water northward from the tropics, releasing that heat to the atmosphere over the North Atlantic and northwestern Europe, and then returning cold, dense, saline water southward at depth. The Atlantic Meridional Overturning Circulation, or AMOC, is the fundamental reason Western Europe enjoys a climate far more temperate than its northern latitude would otherwise dictate. London, for instance, shares a similar latitude with Calgary, yet its weather is dramatically milder, a direct result of the heat transported northward by this powerful ocean current. This vast oceanic conveyor belt, however, appears to be faltering. A convergence of evidence from ocean temperature and salinity measurements to direct monitoring via the rapid array and reconstructions from sediment cores points toward a troubling conclusion. The AMOC is currently at its weakest state in at least 1,000 years, and possibly much longer. The primary cause is the increasing flow of fresh water from melting Greenland ice into the North Atlantic. This influx lowers the salinity and, therefore, the density of the surface water, which must sink to power the circulation. Less sinking leads to a weaker overturning, which in turn diminishes the transport of heat. A 2021 study in Nature Climate Change, which analyzed historical indicators, suggested the circulation might be nearing a critical tipping point, beyond which it could collapse into a much weaker state. This conclusion remains a subject of active scientific debate. Some researchers maintain that the system is more resilient than these proxy indicators imply, viewing a full collapse within this century as unlikely under current emissions scenarios. While the debate over a potential collapse continues, the underlying trend of a weakening AMOC in response to Greenland's melt is not in dispute. The crucial question that remains is just how close the system is to a dangerous threshold. So, why is the state of the AMOC so critical to the scenario projected for 2026? A weakening circulation fundamentally alters the distribution of heat across the Atlantic Basin, directly influencing moisture and temperature conditions over the Amazon and tropical Africa. As we have explored, a warm Atlantic is a key amplifying factor in the multi-basin configuration that makes 2026 potentially more hazardous for tropical forests than a standard Pacific El Niño event. The weakening AMOC contributes to this warming by reducing the northward export of tropical heat. This process effectively traps warmth in the tropical Atlantic that would otherwise be redistributed across the globe. It is a profound feedback pathway, one that forges a direct link between the melting of distant ice sheets and the growing stress on the world's vital rainforests. Our focus now shifts to the Greenland and West Antarctic ice sheets, the two largest reservoirs of land-based ice on our planet. While their potential to raise sea levels is the most widely discussed consequence of their instability, their role in this cascading story of tipping points extends far beyond the coastlines. The Greenland ice sheet is already losing mass at an accelerating pace, and its meltwater is the principal force driving the weakening of the AMOC. Meanwhile, several analyses from the past 5 years suggest that key glacial systems in the West Antarctic ice sheet have already passed a threshold of committed retreat. This means that even if global warming were to halt today, the dynamics already in motion would ensure continued retreat and mass loss for centuries to come, a commitment that is irreversible on human timescales. The connection from this massive ice loss back to the carbon sink story is twofold. It runs through the AMOC pathway and through the overall acceleration of warming caused by the ice albedo feedback. As ice disappears, less solar radiation is reflected back into space. More heat is absorbed at the Earth's surface, which in turn places greater stress on every temperature-sensitive system, including the tropical forests. Arctic permafrost presents what is perhaps the most direct parallel to the story of the tropical carbon sink, as it is itself a massive carbon reservoir that is already beginning to fail. The permanently frozen soils of the Arctic and subarctic hold an estimated 1.5 trillion tons of organic carbon, which has accumulated over millennia in cold conditions that prevented decomposition. But as Arctic temperatures rise at a rate 2 to 4 times the global average, a phenomenon known as Arctic amplification, the permafrost, is thawing. This allows microbes to colonize the soil and break down organic carbon that has been frozen for thousands of years, releasing carbon dioxide and methane into the atmosphere. Methane is an especially potent greenhouse gas, roughly 80 times more powerful than carbon dioxide over a 2-0-year period. This permafrost carbon feedback is not a future possibility, it is already underway. Monitoring networks across Siberia, Alaska, and Canada show that permafrost is thawing and releasing carbon at rates that exceed what most models had predicted for current temperature levels. The system is not waiting for a future warming threshold. It is responding now, adding to atmospheric greenhouse gas concentrations in ways that go beyond human fossil fuel emissions. The failure of the tropical carbon sink and the thawing of Arctic permafrost are not the same phenomenon. They operate through different mechanisms, on different timescales, and in different parts of the world. Their impacts, however, are additive. Both are vast natural reservoirs that are transitioning from being net absorbers of carbon to becoming net emitters. And both are undergoing this transition in response to the same underlying global warming that an event like the 2026 Super El Niño would only accelerate, pushing these systems further from stability. The Indian summer monsoon completes this picture of interconnected systemic stress. This vital weather pattern is driven by the temperature difference between the rapidly heating Asian landmass and the cooler Indian Ocean. An El Niño event weakens the monsoon by reducing this temperature differential. The weakening AMOC also affects it by altering Atlantic sea surface temperatures, which in turn disrupts the global atmospheric circulation patterns that establish the monsoon. Adding another layer of complexity, aerosol pollution from industrial activity and biomass burning across South and Southeast Asia further disrupts this delicate balance. As we've discussed, in the context of agricultural fragility, the stability of the monsoon underpins the food security of more than 1 billion people. Its instability is therefore not merely an ecological problem, it is a human systems problem of the highest order. The potential failure of the carbon sink, which a 2026 Super El Niño could trigger, sits at the very heart of this network of interconnected systems. This is not because it is necessarily the largest or most dramatic of the tipping risks, but because it serves as the crucial connection point, the thread that links the fate of the forests to the story of the ice sheets, the ocean currents, and the monsoon. A weakened carbon sink means a faster accumulation of atmospheric carbon dioxide. Faster accumulation leads to faster warming, and faster warming creates a self-reinforcing cycle. More melt from Greenland means a weaker AMOC, which leads to a warmer tropical Atlantic, which in turn places even greater stress on the world's forests. It is here, at the intersection of these vast Earth systems, that the true nature of the challenge becomes clear. Each system does not act in isolation. They are all threads in a single, complex, and rapidly changing planetary tapestry. A rise in global temperature triggers a cascade of planetary responses. Accelerated warming leads to accelerated permafrost thaw, which releases more methane, which in turn drives even faster warming. At the same time, this warming contributes to greater mass loss from the ice sheets, causing sea levels to rise. This, in turn, creates more coastal disruption and places immense pressure on human systems that are already under stress. None of these critical feedback loops operates on the short timescale of a single weather event like El Niño. If this cascade is already in motion, it will unfold over decades. This long time frame is precisely what makes the danger so difficult to communicate and so easy for many to dismiss, as any single year may not seem to constitute a full-blown emergency. The crisis does not announce itself with one singular, catastrophic event. Instead, it reveals itself through a gradual but quickening shift in the baseline conditions of our entire planetary system, a shift that, once it has advanced far enough, could become self-sustaining in ways that no future human action can completely reverse. This is why the question of the carbon sink's recovery after 2026 is not merely a technical detail for specialists. It is a question that forces us to ask which of two profoundly different planetary futures we are now heading toward. One path is a trajectory that maintains enough stability in Earth's systems for the clean energy transition to be truly meaningful. On this path, our emissions reductions would successfully translate into reduced warming. The mathematics of our carbon budget would remain coherent, and the planet's major tipping elements would stay below their thresholds long enough for civilization to adapt. The other trajectory, however, leads to a period of coupled system destabilization. Here, the feedbacks between tipping elements would begin to drive warming faster than any human emissions cuts could possibly offset. In such a world, we would no longer be racing primarily against our own emissions, but against the Earth system's own internal, accelerating dynamics. These are not equivalent outcomes, they are entirely different worlds, and the difference between them may depend, in a very meaningful way, on what the carbon cycle data reveals in 2027 on whether the great forests hold on and whether the planetary system that has been protecting us is still able to do so. We have stood at a similar precipice before, on two separate occasions, and both times the system demonstrated its resilience. In 1998, as the atmospheric carbon dioxide growth rates spiked and vast Indonesian peat fires were finally quenched by the returning monsoon rains, scientists watched the incoming data with a mixture of relief and deep unease. The carbon cycle did recover. The growth rate fell back toward its previous trend line, and the event was catalogued as a severe, yet ultimately temporary, disruption. The system had been pushed to its limit, but it had returned. A similar story unfolded in 2016. As the OCO-2 satellite orbited above, it recorded a global carbon dioxide growth record of 3.05 parts per million. Yet in the following year, the data showed a significant drop back toward normal levels. The Amazon regreened as the rains returned. The terrible fire season in Indonesia eventually subsided, and an anomalous soil respiration event in Africa faded as temperatures normalized. The carbon sink appeared to come back online. The response was one of cautious relief, a signal to update the models and move on. But what if the past is no longer a reliable guide? Both of those recoveries occurred in a world that was fundamentally different from the one we inhabit today. They happened at a time when the southeastern Amazon was still a functioning carbon sink. They happened before the Indonesian peatlands had been burned through twice in just 2 decades, on top of 40 years of drainage. They occurred when the soil moisture reserves of the Amazon had not been so severely depleted by the worst drought in recorded history only a few years prior. And critically, They happened before the background warming of the Pacific, Atlantic, and Indian Ocean basins had all reached the levels we see today. The year 2026 will therefore be the first crucial test of the Earth system under these entirely new circumstances, conditions against which our models have not been extensively validated, and for which we have no clean historical analogue in the instrumental record. We are, in all relevant respects, entering genuinely novel territory. The observational tools we now possess are extraordinary. The OCO2 satellite is still operational and has been joined by newer instruments with even better spatial resolution. A comprehensive network of ground-based atmospheric monitoring stations now spans the Amazon, covers Southeast Asia, and reaches into the Congo basin. Geostationary satellites track fire events in near real time, while networks of flux towers continuously measure the exchange of carbon between the atmosphere and specific forest locations. Should the carbon sink begin to fail in 2026, we will know about it faster and in far greater detail than we knew anything about the events of 1997 or 2015. The data will be unambiguous, and the geographical fingerprinting of the sources will be precise. Yet, what we do not know, what no observational network, no matter how sophisticated, can tell us in advance, is the true limit of the system's resilience. We cannot know the precise threshold at which the ratchet effect produces an incomplete recovery instead of a full one. We do not know the exact percentage of deforestation at which the Amazon's moisture recycling begins an irreversible decline, or the specific increment of warming that prevents Indonesian peatlands from suppressing fire, regardless of rainfall. These thresholds exist. The science tells us they must. But they are not labeled. They do not announce themselves. They are simply crossed, and only then are they recognized in the data, at which point the entire conversation changes in a way that cannot be undone. The 2026 El Niño will be documented exhaustively. The stories of floods will be written, the maps of drought will be published, and the assessments of economic damage will be compiled. The growth rate of carbon dioxide will be measured with exacting precision at Mauna Loa and dozens of other stations around the globe. And then, sometime in 2027, researchers will publish their findings on what the carbon cycle data from 2026 truly shows. That data will reveal one of two realities. It will either show another severe but ultimately temporary disruption, another spike, another recovery, another update to the models, another narrow escape, or it will show something profoundly different. It might show a spike in emissions that does not fully retrace its path, a growth rate that drops after the event but settles onto a measurably higher baseline than before. It could reveal a southeastern Amazon that is no longer recovering its function as a carbon sink, an Indonesian fire signal that is larger than in 2015, despite improved suppression efforts, or a new, troubling signal from the Congo that was absent in the last event. Such a compound failure across multiple systems would add up to a weakening of the global carbon sink that is not consistent with our model's predictions of a full recovery. If this second scenario is what the data shows, the worlds of climate science and climate policy will be forced to reckon with a reality they have long been reluctant to confront. For decades, a vast natural buffer has silently absorbed half of all human emissions, but we may be approaching a time when its reliability can no longer be taken for granted. This isn't about an overnight collapse, but a gradual degradation that could render our climate calculations obsolete. Such a shift would not be a minor scientific detail. It would represent a fundamental change to the operating principles of the global climate response. Every carbon budget, every net zero timeline, and every scenario used in international negotiations is built upon the assumption of a stable carbon sink. The data arriving in 2026 will serve as a critical test of this foundation. We have witnessed this system falter before, in 1997 and again in 2015. Yet each time it recovered, allowing us to update our understanding and continue. What makes the situation surrounding 2026 so different is the unprecedented strain on the system. For the first time in the era of modern observation, we are examining a planetary system that has been pushed harder, stressed for longer, and damaged more severely than at any point in the history of human-induced climate change, with far less time to recover between shocks. This is a test of true resilience. We are about to discover whether the endurance of the Amazon, the Indonesian peatlands, the forests of Africa, and the ocean's surface is as robust as we have hoped, or if it has been a quietly diminishing resource that we have been spending down without realizing it. For centuries, perhaps even longer, the world's tropical forests have been absorbing the consequences of human activity. These are extraordinary, ancient ecosystems, profoundly adaptive and resilient. The carbon stored within the peat of Borneo, for instance, has remained locked away since before the rise of the Roman Empire, while the trees of the intact Amazon have cycled water and carbon since before the first human settlements. They are not fragile systems poised to collapse after a single dry season. Yet, they are not infinite. Their capacity for recovery appears to be waning, and the rate at which we are demanding their resilience through warming, drought, deforestation, and the compounding frequency of extreme events is now greater than at any other time in history. Current forecasts indicate a 61% probability of an El Niño onset by July, with models predicting a temperature anomaly between +2 and +2.75 degrees Celsius in the critical Nino 3.4 region. As satellites and monitoring networks record the data, scientists are watching the numbers closely. Somewhere in the Amazon, in a forest that has been struggling for the past 2 years, in soil drier than it ought to be, and in a watershed where rivers have fallen to record lows, the trees are waiting for the rain. The historical data shows that they have always recovered. This fact is perhaps the most important thing to remember as we observe what unfolds. However, it is also the one thing we can no longer afford to simply assume will happen again.